Hello, I am Shikha Malhotra. Today's topic is going to be digital logic circuits, and we are going to cover in it a few things like integrated circuits, encoder decoders, multiplexer demultiplexers, and registers. When we talk about digital computers, we all understand and hear the word integrated circuits or the IC. Let's see what it is. It's manufactured using a silicon material which is mounted either on a ceramic or a plastic container, which we commonly call as a chip. The basic components of this chip is an electronic circuit, and it's made up of a number of digital gates. These various gates are interconnected on the IC to form the required circuitry. So the types of ICs that we use, let's start from the smallest one, which is called as the SSI or the small scale integration device. As the name says, small. So the number of devices that are connected on it are gates. The inputs and outputs of these gates, they are connected directly to the pin of the package. The number can be usually less than 10, and they are limited by the number of the pins that are available on the IC. So that's why the name small. The next one is a medium scale integration or the MSI. With the medium word, we increase the complexity from 10 to 200 gates on this package. The components that are included here are decoders, adders, and registers. Coming to the next one, which is a large scale integration device. Again, as the word says large, it contains about 200 up to few thousands of gates in a single package. The basic components of the LSI device include digital systems such as processors, memory chips, and programmable modules. The most commonly used in today's time is a very large scale integration device or the VLSI. This type of device will contain thousands of gates within a single package. The most common example is a simple microcomputer chip. Now let's see where are these used. All these that we have learned, the digital integrated circuits are also classified by the specific circuit in which they belong, and they belong to a digital logic family. Each technology has its own basic electronic circuit and functions to perform. Let's start off with the very first one, which is a decoder circuit. By the name it says decode, so it's a combinational circuit that changes a binary information into 2 to the power n output lines, and that's why it's known as a decoder. The binary information is passed in the form of n input lines, and the output will be 2 to the power n bit codes for that relevant binary information that went into it as an input. The n to m decoder has n inputs and m outputs, so we commonly call it as n cross m decoder. At any time, only one input line is activated for the simplicity. The produced 2 to the power n bit output code is equivalent to the binary information from that input. Let's look at the circuit. As we know, n to 2 to the power n decoder. So we see on the input side, you have n lines, and on the output side, you will have 2 to the power n output lines. Let's take an example of a 3 to 8 line decoder. 3 inputs converted to 2 to the power 3, which is equal to 8 outputs. So a 3 to 8 line decoder will have 3 data inputs, A0, A1 and A2 in this example that we are taking here, and these are decoded into 8 outputs, each output representing one of the combinations of the 3 binary input variables. The 3 inverters will provide the complement of the input, and each of the 8 AND gates generates one of the binary combination. Let's look at the block diagram, which represents exactly what I just said. 3 inputs, A0, A1 and A2, and you have 8 outputs starting from Y0 to Y7. So it's a 3 to 8 decoder block diagram. How does it function? It's also called as a binary to octal decoder, because we know these are the number of bits we need to represent a binary or an octal digit. There are a total of 8 outputs, Y0, Y1, 2, 3, 4, 5, 6 and 7, and 3 inputs, A0, A1 and A2, which we just saw in the block diagram. Commercial decoders will include one or more inputs, which is called as the enable input, represented by E, which is used to control the operation of the circuit. The decoder is enabled when E is equal to 1 and it is disabled when E is equal to 0. Let's look at this in the truth table. If you look at the very first row, where E is equal to 0, all the three inputs A0, A1 and A2 have a cross, which is a don't care condition, and you see that in the output side, Y7 to Y0, all of them are zeros. When E is 1, that means it is enabled. That's when we will see all the inputs having some or the other value and the output having a relevant value according to the inputs that have gone in, and each representing one octal digit. So when the E is equal to 0, all the outputs are equal to 0 regardless of the values of the other three data inputs. The three X's that I just mentioned to you in the table will designate the don't care conditions. When the E equal to 1, the decoder operates in a normal fashion, which I just explained. For each possible input combination, there are 7 outputs that are equal to 0 and only one is equal to 1, which is actually equal to the value that the octal digit takes. The output variable, whose value is equal to 1, represents the octal number, which is equivalent to the binary number that is available in the input lines, and hence we call this decoder as a binary to an octal decoder. The logical expression of the terms that we get out of the truth table are very clearly visible to us here. Each term Y0 to Y7 has a term written in front of it which represents an octal number. The same expression has been depicted in this logical circuit with the help of the gates that we see. So you see an input A0 in the direct form and also in the complemented form going through the inverter. Similarly for A1 and A2, and on the output side we have each output coming out of an AND gate. That's how a decoder functions, and at any given point of time the combination of the bits that are there in A0, A1 and A2 would have only one of these gates active, and we will receive one octal number as an output of this. Let's take another example, which is a little deviation from what we just saw. Sometimes instead of an AND gate, we may also have circuits which are constructed using NAND gates. The purpose is very clear, that when we use a NAND gate instead of an AND gate, the inverted output is also available to us right there, and it becomes economical because we have replaced an AND and an OR gate, just NOT gate, by a simple NAND gate there. So automatically we have the inputs directly in the complemented form also available to us. A 2 to 4 line decoder with an enable input constructed with NAND gate is going to be discussed now. Let's take a 2 to 4 line decoder. Again, n is the number of inputs and 2 to the power n is going to be your outputs. So you have 2 inputs, 2 to the power 4 is a 4 output line decoder. There are going to be 3 inputs, A0, A1 and the enable E. 4 outputs, Y0, Y1, Y2 and Y3. For each combination of the inputs, when the enable E is set to 1, one of these 4 outputs will be 1. This is identical to what I just discussed in the 3 to 8 line decoder also. The block diagram for a 2 to 4 decoder is as visible. A1 and A2 are the 2 inputs, E is the enable, and we have 4 outputs from Y0 to Y3. Let's look at the truth table. Similar to what we saw in the 3 to 8, here in the last row you see you have 2 don't care conditions. The remaining is almost the similar as the other one. The expressions that we get out of this are Y3, Y2, Y1 and Y0 and their corresponding values in terms of the E enable, which is 1, and A1 and A0. These expressions are being represented by this logical circuit where we have a inverter and an AND gate here. Let's look at the next circuit, which is an encoder circuit. As we just learnt about a decoder, encoder is the reverse of a decoder circuit. So what does it do? An encoder is a digital circuit that performs the inverse operation of a decoder. Encoder will have 2 to the power n or maybe even less input lines, and the output lines will now be n, which is just the reverse of the decoder. The output lines generate the binary code corresponding to the input values. The objective is to perform a binary operation, which could be an addition, subtraction, multiplication, etc. For example, now we are looking at an octal to binary encoder. This has 8 inputs, one for each of the octal digits, and will have 3 outputs which are going to generate the corresponding binary numbers. This is exactly the reverse of the 3 to 8 decoder that we saw earlier. It is assumed that only one input has a value of 1 at any given point of time, otherwise the circuit will not be able to function and will have no meaning at all. The circuit or the logical diagram, on the left side we see we have 2 to the power n input lines, and on the output side n output lines. Let's take up an example of a 4 to 2 line encoder. In a 4 to 2 line encoder, there are going to be 4 inputs as the name suggests, from Y0, Y1, Y2 and Y3, and only 2 outputs, which is A0 and A1. The 4 input lines, one input line is set to true at a time to get the respective binary code in the output side. This is how it will look: Y3, Y2, Y1 and Y0 on the input sides, and output will have only 2, A1 and A0. The corresponding truth table is represented here, and we see the output sides is going to have a 1 in certain situations, and that can be converted into a statement as A1 is Y3 plus Y2, A0 is equal to Y3 plus Y1, and these equations or Boolean expressions are being represented in a logical circuit using the gates here. So if you see the first gate, output A1 comes from Y3 and Y2, and look at the second gate, the output A0 comes from the input Y3 and Y1. Let's look at the next circuit, which is the multiplexer. How is it going to be different from what we have learnt till now? A multiplexer is a combinational circuit which receives binary information from one of the 2 to the power n input data lines and directs it to a single output line. The selection of a particular input data line for the output is determined by a set of selection inputs. A 2 to the power n to 1 multiplexer has 2 to the power n input data lines and n input selection lines, whose bit combinations will determine which input data are selected for the output. A multiplexer is a combinational circuit that has 2 to the power n input lines and a single output line. The multiplexer is a multi-input and single output combinational circuit. The binary information is received from the input lines and is directed to the output line. On the basis of the value of the selection line, one of these data inputs will be connected to the output. Unlike the encoder and decoder, there are n selection lines and 2 to the power n input lines also. So there is going to be a total of 2 to the power n possible combinations of input here. If you take an example of 2 to the power 2 cross 1 multiplexer, there are only 2 inputs, that is A0 and A1. There is going to be one selection line, that is say S0, and a single output, say Y. On the basis of the combination of inputs which are present at the selection line S0, one of these 2 inputs will be connected to the output. Look at the block diagram. So a 2 cross 1 multiplexer, we have 2 inputs A1 and A0, a select line S, and an enable E also there. However, the output is going to be only one, which is Y. The truth table shows S0 and Y, which is input S0 and output Y. Input is 0, we have an output A0. Input is 1, we have an output of A1. The expression Y is equal to S0 dash A0 plus S0 A1. The logical circuit is going to be similar. We have the gates available to us, and that is how it is being represented. Let's take an example of a 4x1 multiplexer. In a 4x1 multiplexer, there are a total of 4 inputs. As the name suggests, we will have A0, A1, A2 and A3. 2 selection lines because we have 4 inputs now, S0 and S1, and only one single output, which is Y, because the name of the multiplexer suggests 4 inputs, 1 output. On the basis of the combination of the inputs that are present at the selection line S0 and S1, one of these 4 inputs are connected to the output. So look at the diagram here. Input side, you have 4 inputs, A3, A2, A1 and A0. 2 select lines, S1 and S0, to control the 4 inputs that we have here, and 1 output, Y. The truth tables, again the inputs are going to be S0 and S1 because that is what controls the other inputs, and the output is Y in terms of A0, A1, A2 and A3, and basis this truth table, we have the expression in front of us. Y will be S1 dash, S0 dash, A0 plus S1 dash, S0, A1 plus S1, S0 dash, A2 plus S1, S0, A3. Similarly, the expression has been has been represented by this logical circuit. Basis the expression that was given to us, we have the corresponding AND gates, inverters and an OR gate being used. A very simplified form. You see 2 inputs S1 and S0, 4 inputs A3, A2, A1 and A0, each going into the respective inverter or the AND, and the output coming out as a Y out of this OR gate. So let's do a recap of the multiplexer circuits. We have learnt about decoder and encoder. They belong to one kind of circuits. We are now going to look at multiplexer circuits because they are a little different from what we have learnt in the decoder and encoder circuit. So why we need to revise this is because it gives us a very clear understanding of what we are reading about, and is in continuation of the next topic, which is going to be a demultiplexer circuit. So we have a club of encoder and decoder, and we have a club of multiplexer and a demultiplexer. So when we talk about a multiplexer circuit, it's different from decoder and encoder because it is a combinational circuit, of course, but here it receives a binary information. And in this, we have 2 to the power n data lines, which are the inputs, and you have only one output line, which is not what we had in the case of a decoder or an encoder. The selection of any of these input lines would be dependent on a set of selection lines. What are these selection lines? Depending on how many input data lines we have, we will have that many number of selection lines. These are usually called S or represented as S on your circuit. So if I look at a 2 to the power n to a 1 multiplexer, which means 2 to the power n are the input data lines, and n input selection lines will be required for this. So if I am taking as 2 to the power 2, which means 4 to 1 multiplexer, I will have n input selection lines, which means 2 input selection lines, whose bit combinations will determine which input data are selected for the output. That's how it goes in the digital circuits. We understand that, and so a clarity on this. Let's assume if I have 2 to the power 3, which is 8 input lines, or 8 to a 1 multiplexer, I will have 3 input selection lines to control these bit combinations. So looking at this, a multiplexer we just saw is also known as a multiple input and a single output combination circuit. The binary information that is used here is received from the input circuits or input lines and are directly sent to the output line. On this basis of the selection lines, what values the selection line has, one of these data inputs will be connected to the outputs, and that's what a selection line does. It helps to identify on what output is going to be sent down to the output line. However, different from the encoder and decoders, there are n selection lines and 2 to the power n input lines. So there is going to be a total of 2 to the power n possible combinations of the input. which is not the case in an encoder or a decoder circuit. Let's take an example. If we have a 2 cross 1 multiplexer, there are going to be only two inputs, A0 and A1. If you remember, I mentioned 2 to the power n. So here it is 2 to the power 0, or which is equal to 1. So I will have one selection line, which is S0, and there will be only one output, which is typical of a multiplexer circuit, which is denoted by Y. On the basis of this combination of the inputs, which are present at the selection line S0, so the inputs that are going on A0 and A1 and what is available on the selection line S0, one of these two inputs will be connected to the output, and that's the part that an S0 or the selection line plays here. So this is how a multiplexer will look. You have all of the components that are used here, input lines A1 and A0, select line S, enable E, and an output line Y. The truth table, dependent of course on S0, what input is going to S0 will help the A0 or A1 to go to the output line Y, which is what I mentioned. Basis what is the value that the selection line S has, we will have one of the inputs going on to the output line. So we see in this table, when S0 is 0, you have the A0 going as the output. When we have S0 as 1, we have line A1 going as the output. Now corresponding equation has been made or written down. Y is equal to S0 dash A0 plus S0 A1. The similar thing has been represented here with this logical circuit diagram that we see. So the statement that we got, or the Boolean expression that we got, has been represented a very simple diagram which just uses the inverter and the OR gate to represent or get the output of this multiplexer. Take an example of 4 cross 1 multiplexer. Since it is 4 is 2 to the power 2, so we will have two selection lines here, 4 inputs A0, A1, A2 and A3, two selection lines S0 and S1, but the output always remains 1, which is Y. So on the basis of the combination of the inputs that are present here at the selection line S0 and S1, one of these 4 inputs are going to be sent to Y. That is the purpose of having the selection line, which we've been discussing earlier also. So the block diagram, similarly, 4 input lines, 2 selection lines, 1 output line, Y. Truth table, if you see, we have 2 inputs, S1 and S0, which are the selection lines. Basis of the values that these take, we have the output Y. So when S0 and S1 both are 0, the output is going to be A0. So line A0 goes to the output. When the second statement, S1 is 0, whereas S0 is 1, we have the output as A1. Third one is S1 is 1, S0 is 0, output is A2. And when both S1 and S0 are 1, the output would be the line A3. So it's very clearly obvious how both the selection lines S1 and S0 are controlling what goes to the output in this diagram, in this truth table. Also, the same truth table has been expressed in the form of the expression above. Y is S1 dash S0 dash A0 plus S1 dash S0 A1 plus S1 S0 dash A2 plus S1 S0 A3. Similarly, we see that same expression has been represented in the form of this block diagram or this logical diagram or logical circuit, simply using the inverters to get the reversed output of S1 and S0. We have the 3 or 4 AND gates and 1 OR gate Y. The expression of S1 could be used either in the direct form or in the inverted form, which is visible from the equation that we have used here.